Hey everyone, my name is Preethi and my project partner John Wright and I are going to share with you our 421 project. We worked with Dr. Moffat to examine the effect of anode intensification on nerve fiber recruitment order. Smaller diameter fibers are activated prior to larger diameter, and this is a phenomenon known as the Henman size principle. However, with extracellular electrical stimulation, the opposite happens, where larger diameter nerve fibers are activated before smaller ones. And so there's a need to be able to selectively recruit smaller diameter fibers before larger ones. And there are several techniques that have been explored in the past. One such technique is called anode intensification, and this is explored in a patent by Lee et al. And the essence of this concept is you apply anodic current in addition to cathodic current to try to reverse the recruitment order. So in a standard electrical stimulation, anodes and cathodes must give out the same percentage of current, but in anode intensification, we inject more anodic current to try to shape the current on the nerve. For example, in the normal case, anodes and cathodes will contribute the same amount. So if we're delivering a 1 milliamp of current, the cathode will have a negative 1 milliamp, and the anodes each will have 0.5 milliamps. We can increase the anodic current, as I mentioned, to 120%, where in the same example, if you were injecting 1 milliamp of current, each anode would now contribute 1.2 milliamps. This technique successfully showed in this patent the reversal of fiber thresholds. On the graph on the left, there are 3 different lines describing 3 different electrode current configurations. On the most bottom, the 50, negative 150, anode arrangement, we see the standard extracellular electrical stimulation, or we see what we would expect from extracellular electrical stimulation, where the larger fiber diameters have a lower threshold, and thus are activated faster than the smaller diameters. However, as we inject more anodic current, for example to 120, we notice that smaller fiber diameters are actually being recruited prior to the larger ones, meaning that the smaller fiber diameters have a lower threshold. These results were what we were trying to replicate in our project, and we will go into next the methodology of how we went about that. So we attacked our problem with 2 different aims. The first aim was to generate extracellular potentials from various different anode-cathode arrangements. We used Python to generate a script to create these potentials for us. We could modify various different parameters, such as the distance between cathode and anode, distance from the nerve to the electrodes, and even the current percentages that we wanted to change between the cathode and the anodes. We assumed that this was an infinite volume conductor, and if we assumed linearity, homogeneity, we could superimpose each of the potentials that were generated by these electrodes together, and we used this formula. We had the output of an array that contained these potentials, and we also saved the potentials to text files that we could import into Neuron later. We visualized these potentials by using a heat map, and the heat map shows a brighter color when there is more or higher potential present.
Once we had the potentials mapped out in such a way that they could be accessed either within Python as an output of the function or directly in Neuron as the output of a file, we were able to move on to our next aim, which was to insert these potentials into a simple excitable nerve fiber model to test whether or not we could induce fiber order recruitment reversal. To pursue this, we first created a function that would allow us to generate a simple fiber. This simple fiber was not necessarily biologically equivalent, as it was a single long homogeneous fiber with no myelination, no changes in diameter, very basic electrical principles that were injected using the insert Hodgkin-Huxley and insert extracellular commands from the neuron software. So our Python command would call the Hawk language necessary to create those, and we were able to alter the fiber diameter, going from 3 micrometers up to 16 micrometers. We used values that would correspond to the MRG paper that we utilized later. So we also were able to step through the stimulation. So we could take this fiber and step through different amplitudes of current that were injected, starting very low and automatically going up stepwise until an action potential was detected. This was done by putting in all the factors that Preethi talked about, the distance to the fiber, the distance between the electrodes, the intensity of the anode-cathode arrangement, and we were able to automatically loop through using Python to detect whether or not an action potential was induced. This chart shows maybe a electrical excitation that would have been caught by the automatic thresholding of our software that would have then recorded this as an action potential to give us the threshold graphs that we will show later. Once we had the 2A version of the AIM done, we moved on to a more complicated version using the MRG nerve model. We broke this up into two parts so that in the first, with the electrically simple model, we could see whether or not the behaviors that we would expect were occurring. The simplicity of the model allowed us to check that the parameters we were utilizing altered the outputs in an expected manner, and it also allowed us to get a hold of the software. Once we had all that sorted out, we downloaded the MRG model. It's a fairly widely used model from 2002 that was developed here at Case and was talked about in class. The model has proven to be a fairly accurate representation of many of the properties of the mammalian nerve fiber. And so we use this as the basis to explore whether or not our model was able to induce fiber order recruitment reversal. Initially, our approach was to be fairly similar to what we did in AIM 2A. We would create a lot of different fiber diameters, and automatically loop through the software to give us our threshold graphs. During this process, we encountered several software difficulties that caused us to change exactly how we approach that. Initially, we were going to apply extracellular current along the fiber, as we did in 2A, at each point along the MRG model axon. However, due to the way our code interacted with the MRG code, this caused errors. To get around that, we inserted current at each node of RON-VA. We justified this change in that in many models of the nerve, the myelin is thick enough that it can be treated as having incredibly high resistance, sometimes in some models bordering on infinite. With these assumptions, we were able to say that the current would be injected primarily, or in this case solely, at the nodes of RON-VA, and we were able to calculate the currents to inject based on the voltage and potential field output by our voltage function. Additionally, we had to find the manual threshold because of the interaction between the MRG model and our software. We had difficulty automatically looping, so we would manually find the thresholds, and that was how we got these results.
The graph on the left describes the effect of anode intensification on a simple excitable fiber. There are 4 different lines here, and each of them correspond to a different anode current percentage. Across all 4 of these conditions, we observe that fibers with a larger diameter will have a lower activation threshold. This means that fibers with a larger diameter will be recruited first, prior to the smaller ones. This result does not match up with the patent's results because there is no reversal in fiber threshold that we can see. However, we notice that as more anodic current is applied, the lower the activation threshold is across all fiber diameters. And this result is something that was shown in the patent.
We did not see anything that remotely resembled either the patent or our expected behavior in our MRG spinal motor neuron model. What the results we got from this model showed that fibers of a greater diameter required a higher threshold, and this is not how our understanding of the electrical stimulation of the nervous system would lead us to believe. Additionally, the intensity, as we varied the conditions for the cathodes and anodes, we saw that eventually it would become intense enough that we saw almost no difference in activation across the fiber diameters. While this does not square with our understanding of how the electrical stimulation of the body should work, we believe that this is due, in part at least, to how we electrically stimulated using the I-clamp methodology. Previously, I mentioned that due to difficulty with the code, we took the approximation of, instead of using pure extracellular potentials across the fiber, we applied equivalent I-clamps at each of the nodes of RON-VA in the model. We believe that using this I-clamp methodology may not have been equivalent to the extracellular stimulation, either because our conversion math was incorrect, or the way in which neuron is applying this function was not what we understood it to be. So, as such, no fiber reversal was observed in either model, but the simple excitable fiber had a more biologically equivalent behavior than our more complicated and theoretically better model in the MRG spinal motor neuron.
Because our MRG model wasn't doing what we had expected it to do biologically, we decided to use the simple excitable fiber to explore different parameters and see what effect anode intensification would have on recruitment order. First, we looked at the effect of distance between the nerve fiber and electrodes. We noticed that a greater distance between the nerve and the electrode had a higher current threshold for activation. This relationship makes sense because the closer the distance between the fiber and electrode, the less current you would need to apply to induce an action potential in the nerve fiber. Next, we looked at the effect of distance between the cathode and anodes. And we observed that a greater distance between the two electrodes presented a lower current threshold of activation across all fiber diameters. One possible explanation for this phenomena is that the anodic current would stifle the cathodic current when it was closer in electrode distance, which would lead to a higher activation threshold to initiate an action potential.
So in conclusion, I wanted to talk about some of the limitations and future steps we would need to do to make our preliminary results more usable. In terms of the limitations of the model, the simple excitable fiber is not a biologically relevant model. It lacks ion channels, it lacks myelination. Its dynamics are probably not equivalent to many of the nerves that we would want to stimulate in the peripheral or central nerve, or peripheral or spinal cord. While these errors are slightly less in the MRG model, it is still not a perfect biological equivalent. And the way in which we applied the stimulation via the I-clamp seems to have caused some form of aberration in our results. So those limitations would be the first things to possibly look at in any future moves with this model to improve upon. So in the future study, we would want to fully integrate the extracellular stimulation with the MRG axon model, allowing us to get rid of the I-clamp approximation we utilized. Additionally, we would want to test the effects of anode intensification on other models, so other neuron models taken from the database available online. The reason we'd want to do this is to understand what biophysical mechanisms may be leading to recruitment order reversal. We know that in both the patent and in a separate verification done by Dr. Moffat, modeling seems to allow for the demonstration of this fiber recruitment reversal. However, our preliminary states didn't really show that, so it didn't let us start to explore what different biophysical modeling mechanisms might cause it to happen. So these would be the jumping off points. Just a last closing takeaway point. There is a patent that seems to indicate that recruitment fiber size can be reversed in terms of recruitment order. Our model did not show that, but it did show a lot of biological behavior in that if you move the current further away, it takes more of it to activate the fiber. If you push the anodes and cathodes further away, it's easier to excite the fibers, and that the larger the diameter, the easier it is to recruit through extracellular stimulation. Thank you for your time, and have a good rest of your day.